During the discussion today, we will see how to obtain the equation for a graph like this. This looks like a sine curve. Therefore, these kinds of functions are called sinusoidal functions. This is a graph of a sinusoidal function. Even though it's called a sinusoidal, it looks also like a cosine graph. However, even the cosine graph can be written in terms of a sine function. Therefore, in general, these kinds of waveforms are called sinusoidals. During the discussion today, we will learn how to write down an equation, in fact, a set of equations, all of which will represent the equation that's used to draw this graph. To write down an equation like that, we are going to need a starting point for this sinusoidal. So what is the starting point of this sinusoidal? We know these kinds of curves exist from negative infinity to positive infinity. There is no unique starting point, but we will assume any random point as a starting point of this graph. We will call it a reference starting point. The reference starting point should be selected either at a peak, at a trough, or at the center. When you select a starting point like that, we can quite easily write down an equation taking that point into consideration. If you look at this graph, I have selected 5 points. One point is right here, 1, 7. I can write down an equation for this graph using that point, and that point is at a peak of this graph. If you look at these 2 points, they are on the center line, -1, 0 and 3, 0. I can write down 2 other equations by looking at those 2 points respectively. And then I have 2 more points remaining. One point is right here, the other point is right here. Those 2 points are in the trough of this graph. Using each of those 2 points also, I can write down 2 other equations to represent this graph. By using all 5 points given, I can actually write down 5 different equations to represent this very same graph. In fact, a graph like this can have infinite number of equations. I can select another point somewhere here. I can select this point. I can select this point. I can select this point. Likewise, I can select any such number of points from peaks or from the center line or from the trough. When I select those points, with each point I can write down a unique equation. However, it's advisable that we do not go that far away from the y-axis. For example, if you go more than one period away from the y-axis, most likely you are kind of repeating the exact same equation with just one more period being added, which has to be seen as redundant. Therefore, we will not go that far away. Instead, we will stick very close to the y-axis, which means we will only use these selected points and write down just 5 equations for this graph. Remember, once again, each of those 5 points is going to be considered the starting point of this graph. And then those starting points are going to be compared against the basic sine curve or the basic cosine curve. And also we can compare those points against the reflected basic sine curve and the reflected basic cosine curve. We need to identify the behavior around a selected point, and if it looks like the basic sine curve, we can write down an equation using sine. If it looks like reflected basic sine curve, we're going to write down an equation using a negative sine function. If the behavior around the selected point looks like the basic cosine curve, we are going to write down an equation using the cosine function. If the behavior around that selected point looks like a reflected cosine curve, we are going to write down an equation using the negative cosine function. So, before working on all of that, we will quickly look at the basic sine curve, the reflected basic sine curve, the basic cosine curve and the reflected basic cosine curve. Right here, I have the basic sine curve whose equation is y equals sine x, and the reflected basic sine curve whose equation is y equals negative sine x. For those basic curves, we always consider the starting point to be the point where the graph intersects with the y-axis. For the basic sine curve and also for the reflected basic sine curve, the starting point is actually at the origin because that's where the graph intersects with the y-axis. If you look at the behavior for the basic sine curve, whose equation is y equals positive sine x, within a neighborhood of that point of intersection, this is the behavior of the graph. It's climbing up. Within a neighborhood of the starting point of the reflected basic sine curve, the behavior looks like this. It looks like climbing down. Next, we will look at the basic cosine curve and the reflected basic cosine curve. The equation of the basic cosine curve is y equals positive cosine x. The equation of the reflected basic cosine curve is y equals negative cosine x. Once again, the starting points of basic curves is the point of intersection between the graph and the y-axis. Therefore, for the basic cosine curve, right here is the starting point. For the reflected basic cosine curve, the starting point is right here. Within a neighborhood of the basic cosine curve, the behavior of the graph is like this. It is passing a peak. Within a neighborhood of the starting point of the reflected basic cosine curve, the behavior is like this. It is passing a trough. So, whenever we look at a given sinusoidal, whenever we selected a point as a starting point, then we can see a one-to-one similarity of that point with the starting point of one of the four basic curves that we saw. Then we can write down an equation. For example, let's consider this point. Within a neighborhood of that point, the behavior is like this. That was what we saw in the basic cosine curve. That means by using that point 1, 7 as a starting point for this graph, I can write down a positive cosine equation. Similarly, if you look at this point right here, negative 1, 0, if you consider that as the starting point of this graph, I can see within a neighborhood of that, the graph is climbing up. That means it looks like the basic sine curve, which means by using this point, negative 1, 0 as the starting point, I should be able to write down a positive sine function for this sinusoidal. Similarly, if you look at this point, 3, 0, within a neighborhood of that point, you can see that the graph is going down, which means it looks like the behavior around the starting point of the reflected basic sine curve, meaning I should be able to write down a negative sine equation using that point, 3, 0. Similarly, if you pay attention to this point right here, negative 3, negative 7, I can see that the behavior around that point is like this, which is exactly same as the behavior of a reflected basic cosine curve, which means using this point, I can write down a negative cosine equation for this graph. However, not only using that point, but even if I consider the point right here, 5, negative 7, even around that point, I have that same characteristic like this. So, even using the point 5, negative 7, I can write another negative cosine equation. So, what's the difference between those two? The difference is the distance from the y-axis. The distance to the starting point from the y-axis is called the phase shift. So, if you look at this point, there is a phase shift of negative 3. Or in other words, it is shifted 3 units to the left. If you look at this point, there is a phase shift of positive 5. or in other words, it is shifted 5 units to the right. In addition to those things, there are some other primary differences between the basic curves and the given sinusoidal. If you look at the basic curves again, those were bounded between positive 1 and negative 1. However, this curve is bounded above by positive 7 and bounded below by negative 7, which means the amplitude is different for this graph compared to the basic curves. For this graph, the amplitude is 7. How did we define the amplitude? Amplitude is defined as the distance to the peak from the center line. Also, the amplitude can be defined as half of the height of the sinusoidal curve. The other difference is the period. Period for the basic sinusoidal functions, basic sine curve, for the reflected basic sine curve, for the basic cosine curve, and for the reflected basic cosine curve, the period was equal to 2 pi. Here, the period is different. How did we define the period again? Period was defined as the distance between two consecutive parallel points. So, if I look at the point right here and the point right here, those 2 points can be considered parallel points. It's like this, and right here also it's like this. Therefore, those 2 points can be considered parallel. What's the distance between those 2 points? I can see that the point right here has coordinates of negative 1, 0. The point right here has coordinates of 7, 0. Therefore, the gap between those 2 points is 7 minus negative 1, which will be simplified to become 7 plus 1, which is equal to 8. Therefore, always the period will also be different for these given graphs compared to the basic curves. We are going to write down a generic equation. So what is the generic equation we need? You need to remember the generic equation. This is how the generic equation is written. We write it as y equals a times the trig function. I will simply write it as trig because it's going to be a positive sine curve or a negative sine curve or a positive cosine curve or a negative cosine curve. We don't know what it is yet because it depends on the point that we selected on the graph as the starting point. Therefore, I simply wrote it as trig. And then, open brackets, you will have a b and x minus c, close brackets, and plus d. We will try to identify each of these components. A is the amplitude. So A for this graph should be equal to 7. How did you define that amplitude again? Amplitude is the distance between peak and the center line. Because you can see right here we have the origin. Therefore, the highlighted center line is the x-axis. Please note that there will be no change whatsoever for the amplitude depending on the point that we selected. So A is fixed. How about B? B determines the period. Period is defined as tau, which is a Greek letter spelled T-A-U. Period tau is defined as 2 pi divided by B. From that, I can subject B. So B will be equal to 2 pi divided by tau. What we can see from this graph is tau. So what is the tau for this graph? I need to select 2 points that are parallel to one another. Earlier we selected these 2 points and figured out that the period is equal to 8. Even if you selected 2 other such points, let's say for example this point and the point right here, you will see that the period should be equal to 8. Because if you look at the coordinates right here, they are going to be 3, 0. If you look at the coordinates right here, the coordinates will be 11, 0. Take the difference between those x coordinates. It will be 11 minus 3, which is equal to 8. Therefore, tau, or the period for this graph, is equal to 8. And that also stays a constant irrespective of the starting point that you are going to select. So, if your tau is equal to 8, what should be the value of B? b is defined as 2 pi over tau. Therefore, your b should be equal to 2 pi divided by 8, which simplifies for pi over 4. Now we have figured out b as well. b is equal to pi over 4. Now for this generic equation, I will need a c. Please note that c is the phase shift. Phase shift is the shift of that starting point along the x-axis from the y-axis. So if I selected 1, 7 as the starting point, it is shifted 1 unit to the right. Therefore, c is equal to 1. If I selected the point right here, -3, -7 as the starting point, that point is shifted 3 units to the left. Therefore, c is equal to -3. It is simply the x-coordinate of the selected starting point. If I look at the point right here, c is equal to -1. If I selected the point right here, c is equal to 3. If I selected the point right here as the starting point, c is going to be equal to 5. So c is sensitive to the point selected. So let me write down a quick note there. Therefore, the value of c depends on the starting point. So let me write it down. C depends on the starting point. In fact, it is the x-coordinate of the starting point. However, I have not yet decided a starting point. Therefore, I still cannot say a specific value for c. We will keep it for later reference. Now I need one more value, which is the value of d. d is defined as the vertical shift, or in other words, the shift along the y-axis. In order to determine d, you have to look at the center line. If the center line is the x-axis itself, then d is going to be equal to 0. If the center line is above the x-axis, find the positive distance from the x-axis to the center line, and that will be the value of d. If the center line is below the x-axis, then find the negative distance between the x-axis and the center line. That will be the value of d. Now, if you look at the graph given here, right here I have the center line. That center line is exactly on the x-axis. I know it by paying attention onto this origin right here. The origin is on that center line, which means the highlighted axis is in fact the x-axis. Therefore, for this graph, what should be the value of d? d is equal to 0. There is no vertical shift. Please note that we have found a, b, and d for this graph. They are all going to be fixed. Now all I need is a trig function and the value for c. We can easily find those two also after selecting a starting point. So let me go ahead and select a starting point. How about considering the point right here, 1, 7 as the starting point? As soon as I selected that point, we know that it's shifted 1 unit to the right, which means for that point, c should be equal to 1. The behavior around that point is like this, which exactly is the behavior around the starting point of the basic cosine curve. Therefore, we are going to write down a positive cosine equation around that point. So, how do you write down that equation? Please note that the value of c is equal to 1 for that point. Therefore, we can write down the equation this way. Y should be equal to, first I need to write down the amplitude. Amplitude is equal to 7. The equation we are going to write down is a positive cosine equation. So let me write it as cosine brackets b. b was calculated and we found it's equal to pi over 4. Pi over 4 times x minus, and then I need to write down the value of c. c is equal to positive 1. Therefore, let me write down the one right here, close parenthesis, close brackets. And then I need the value of d. D is equal to 0 for this question. Therefore, this is the final answer, the equation that we obtained as the equation for this sinusoidal function using that point 1, 7. You may use Desmos and obtain the graph of this function and see if it looks like the graph given here. Now we will look at another point. We will consider the point right here. We can see the value of c should be equal to 3 in that place. If you look at the behavior around a neighborhood of that point, we can see it's going down. It's going down means it looks like the reflected sine curve. That means using that point, we will need to write a negative sine equation. Let's go ahead and write it down. For that point, we figured c is equal to 3, and it's going to be a negative sine curve. Once again, right here we have the generic equation. All the other values such as a, b, and d we have found. So how would you write down the equation? The equation will be y equals, the amplitude is 7. The trig function we are going to use is a negative sine function. So let me write down that negative symbol right here, sine. It is just 7 times negative sine. Open brackets, b is equal to pi over 4. Pi over 4, open parenthesis, x minus c. c is equal to 3. Therefore, we write it as x minus 3. Close parenthesis, close brackets, plus d. d is equal to 0 for this problem. Therefore, I do not need to write a d. So this is the equation of the sinusoidal function using that point 3, 0. Once again, you can use Desmos and obtain the graph of this function as well and see if it looks like the graph that we have. Alright, now we will select another point. How about selecting the point right here, negative 1, 0. For that point, c is equal to negative 1. c is simply equal to the x-coordinate of that reference starting point. Then we look at the behavior within a neighborhood of that reference starting point. It's going up like this. This is the behavior that we observed within a neighborhood of the starting point of the basic sine curve, which means using the point right here, we will need to write down a positive sine equation. Alright, let's go ahead and do that. For that point, we figured c is equal to negative 1, and we are going to write down a positive sine equation. Once again, here's that generic equation. Our equation should be equal to y equals a times a is equal to 7. The trig function this time is a positive sine function, sine brackets b. b is equal to pi over 4 x minus c. c is equal to negative 1. Therefore, what should be x minus c? X minus c should be equal to x minus negative 1, which simplifies to become x plus 1. Therefore, it should be pi over 4 times x plus 1, close parenthesis, close brackets, and d is equal to 0. Therefore, this is the final equation obtained using that point for that sinusoidal given. Once again, you can sketch the graph of this function also easily using Desmos and see if it looks like the graph provided. Likewise, let's say I selected the point right here, 5, negative 7. What's the value of c for that point? c should be equal to 5. Within a neighborhood of that point, we can see that the graph has this behavior, which means it looks like the behavior around the starting point of the reflected basic cosine curve, which means we are going to write down a negative cosine equation using that point 5 comma negative 7. So let's go ahead and write down that equation as well. That equation should be y equals a is equal to 7. We are writing down a negative cosine function. So let me write down that negative symbol right here. Cosine, open brackets, b is equal to pi over 4 x minus c, which means x minus 5, close parenthesis, close brackets. D is equal to 0. Therefore, this is the equation of that sinusoidal function using the point 5 comma negative 7. Once again, you can check this equation also with Desmos, obtain the graph of that function, and see if it looks like the graph provided right here. Similarly, the final point indicated in this graph is right here, negative 3 comma negative 7. If I selected that point, c should be equal to negative 3. Within a neighborhood of that point, I can see that the graph looks like this. Once again, we will need to write down a negative cosine function. So how would you write down that equation? That equation should have a c equals negative 3. Therefore, let me write down the equation as y equals a is 7. The function is negative cosine. Let me write down the negative symbol right here. Cosine, brackets, b is pi over 4 for this function, x minus negative 3, which simplifies to become x plus 3, close parenthesis, close brackets, and d is equal to 0. So this is the equation of this sinusoidal function using the point negative 3 comma negative 7. Once again, you can obtain the graph of that function as well using Desmos and see if it looks like the graph provided here. As you can see, I have already written down 5 equations from those 5 points that I selected as reference starting points. I hope this explanation is clear. If I selected some other starting points, I can write down some more equations. However, as you go further and further away from the y-axis, most likely these equations are going to be repeated with integer multiples of the period being added to the equation. Those equations may not be that efficient. Now we will look at the graph of another sinusoidal. For this graph also, we are going to look at the generic equation. So the generic equation is y equals a trig function, bracket, b, x minus c, close parenthesis, close brackets, and plus d. We need to identify all of these pieces. A, b, and d will always stay constant irrespective of the point selected. The pieces that are sensitive to the selected starting point are the trig function and the value of c. We will write down a sine function and also a cosine function. In order to write down a sine function, I need to select a point on the center line. In order to write down a cosine function, I need to select a point at the upper bound or at the lower bound. Before selecting those points, we will try to figure out the values of a, b, and d. What should be a? A is the amplitude. Amplitude is defined as the distance between the center line and the peak. The center line is at y equals 5. The peak right here is at y equals 9. Therefore, the amplitude should be equal to 9 minus 5, which is equal to 4. That's going to be fixed. Next, I'm going to need the value of b. B was defined as 2 pi over tau, where tau is the period. So what's the period of this function? In order to find the period of the function, I need to select 2 parallel points that are next to each other. This point and this point are the 2 consecutive parallel points. If I look at the coordinates right here, Those will be negative 5 comma positive 5. If I look at the coordinates right here, those will be 7 comma 5. Therefore, along the x-axis, the distance between those 2 points is 7 minus negative 5, which will be simplified to become 12. Therefore, tau, or the period, is equal to 12. If tau is equal to 12, this equation gives us that b should be equal to 2 pi over 12, which simplifies to become pi over 6. So let me write down that b is equal to pi over 6. Let's box that result as well. Now I need the value of d. Value of d is defined as the vertical shift. That's the distance between the x-axis and the center line. Clearly, the center line is right here and the x-axis is right here. Therefore, the distance between those two highlighted axes is 5. Therefore, your d should be equal to 5. Let me box that result as well. Now I can select a starting point and identify the trig function that should be used and the value of c. So what's the starting point that you would like to select? If I wanted to write down a sine function, I need to select a point on the center line. If I would like to write down a positive sine equation, I can select this point. If I wanted to write down a negative sine equation, I will need to select the point right here. Because within a neighborhood of the starting point of a negative sine curve, we know that it goes down. Within a neighborhood of a positive sine curve, we know that it goes up. We will go ahead and write down a positive sine equation. So I'm going to select the point right here. I will need the coordinates. The coordinates of that point are negative 5 comma positive 5. Once again, we are going to write down a positive sine equation, and what should be your c? C should be equal to the x coordinate. Therefore, c equals negative 5. Alright, now we will write down the equation. Once again, here's the generic equation. I just need to substitute those values. The equation will be y equals a is equal to 4. The trig function is a positive sine function. Therefore, I will simply write sine, open brackets, b is equal to pi over 6. Open parenthesis, x minus c, x minus negative 5, which becomes x plus 5, close parenthesis, close brackets, plus d. d is equal to 5. This is the equation of the sinusoidal using the point negative 5 comma positive 5. Just like earlier, please draw this graph using Desmos and see if you get a function like this. Now I would like to write down a negative cosine equation. If I wanted a negative cosine equation, I need to select a point at the lower limit. The point that's very close to the y-axis is right here. Therefore, let me select that point. What are the coordinates of this selected point? According to the graph, that point must have an x-coordinate of 4 and a y-coordinate of 1. Therefore, we can quite easily identify that c should be equal to 4 for that point. Because the behavior is like this around that point, we are going to write down a negative cosine equation for that. So let's go ahead and do that. Once again, here's the generic equation. We are going to write down the equation this way. Y equals a is equal to 4. The trig function is a negative cosine function. Therefore, I will write down the negative symbol right here, cosine, open brackets, b equals pi over 6, open parenthesis, x minus c. x minus c is equal to 4, close parenthesis, close brackets, plus d. d is equal to 5. This is the equation of the sinusoidal using the point 4, 1. Once again, try to obtain the graph of this function using Desmos and see if it looks like this. Likewise, you can select many other points also and write down equations. If I wanted a positive cosine equation, I will need to select the point right here. If I wanted a negative sine curve, I will need to select the point right here. All right. If you have any questions, please feel free to let me know. Thank you so much.